I'm in Minitab version 17, and I'm going to have a look at doing the general linear model. So in the previous video I did graphs, and that was from the graph menu here. Now I need to go into the stat menu, and it's a little bit simpler than the SPSS version. We've got our basic stats where you can get your descriptives out and your simple tests, which you won't need for this one, unless you want to do a normality test, of course. Then there's the regression, which would suit last week's material if we just wanted to do a simple linear regression. And the general linear model comes under the ANOVA menu. General linear model, fit general linear model. So the interface is a little bit simpler. I'll just delete that out. We just have to determine what our response is. In this case it would be cholesterol. Our factors are any categorical variables, so in this case it would be gender and abdominal fat. Our covariates are continuous variables which might be related to cholesterol, so that would be weight and age. We won't need the random nested option. If we go into model, this is where it's included all of the variables that we've put in. If we want to check for an interaction term, we will need to add that in. So we could click gender and abdominal fat and then click add interaction. Just leave that set at the default of 2. And you can see that it's then added the interaction term in. Okay. So we don't need the options. I'll just have a look. Coding, that's fine. Leave the stepwise graphs. Now this, I think, is the real benefit, is getting this 4-in-1 residual plot without having to go through and save all the residuals. So this is a real time saver if you're looking at a lot of models. You can also do the residuals versus the variables, which I didn't really talk about in class, but we could look at that at some point in time. If you want to check more closely for curvature, you probably want to check for these, but for the moment you could stick just with the 4-in-1. So the residuals versus the variables you'd probably just do for the covariates, which might be for age and weight. Results, we can just leave all of that at the default settings. And storage, we can save the residuals, but we probably don't need to because it's going to give us the plots anyway. So if you want to do something else with the residuals, you could tick them off and save them here. Otherwise, just leave that at the default. And OK. Now, often I will actually look at the residuals before I look at the output, just because if there's any problems with the residuals, I probably need to fix that first. Excuse me. Before I look too closely at the model. So I'm looking to see if the residuals are approximately normally distributed, that they have roughly the same variance across, and that there's no curvature in the residuals because we're fitting just a straight line to our covariates. So if I make this bigger, you can see that the residuals are approximately normal. I mean, there's a little bit of a hump here, but it's only a small data set. Again, it's a tiny bit wiggly, but not enough to worry about. So I would accept that the residuals are approximately normal. Residuals in observation order, there doesn't seem to be any problem with increasing variance or decreasing variance, so I'd probably accept the assumption that the variances are homoscedastic. And if we have a look at the scatter of the residuals compared with the fitted value, again, there's nothing increasing or decreasing, and there doesn't really seem to be any curvature. So that would imply that fitting a straight line for the covariates is fine. We don't need to add a curved term in there. If we wanted to check that further, that might be where we look at the residuals versus each of the variables individually. So if there was a curved relationship, say a quadratic relationship between cholesterol and age, we would see a curve come out in this graph, but that looks fairly random to me. And again, it looks like a straight line is fine for weight as well. So if I'm happy with the residuals, sometimes you need to close these graphs off when you finish with them just because they do tend to build up. If you're happy with the graph and you want it in your report, it might be worth cutting and pasting it in. So after that, I would go back and have a look at the output. So general linear model, cholesterol versus weight, age, gender, and abdominal fat. It tells me which my factors are. If you happen to get a variable in here which has 27 different levels, that probably means you've accidentally coded a continuous variable, which should be a covariate, and put it in the factor box instead. So you might want to go back and check what you've done. In the analysis of variance table, you can see that we have a whole lot of p-values here, and each p-value is testing a different null hypothesis. The null hypothesis in each case is that there is no relationship between the variable or the factor and cholesterol, given that the rest of the variables are in the model. So for weight, the null hypothesis is that there is no relationship between weight and cholesterol, given that we have already controlled for all these other variables. Now we've got a very low p-value, so that's very strong evidence against the null hypothesis, and therefore we would accept that there is a relationship between weight and cholesterol. And we would also accept that a straight line relationship is adequate because we didn't see any curvature in the residuals. If you wanted to, you could do a separate scatter plot just of cholesterol and weight, and you might also see a curve pop out there. This is just cholesterol and weight without controlling for any other variables. So sometimes a straight line relationship might look reasonable in this plot, but then the curvature actually comes out in the residuals once you control for the other variables. So we've got a rather large p-value, a very large p-value for age. So this is not significant. So age is not related to cholesterol. And I should clarify that this is a made-up data set. It is not real data, so please don't draw any real conclusions about your cholesterol based on this. And then we have the gender is significant, abdominal fat is significant, and there is an interaction term between gender and abdominal fat. So this means that the abdominal fat is having a different effect depending on the gender of the person. And we can have a look at a graph to explore that a bit more. The other parts we might want to look at are the R-squared value, R-squared adjusted value of 94.81%, which is extremely high. You probably wouldn't get this in a real data set. So that says that we are explaining about 95% of the variation in the data with our model, which is very, very high. You can probably, this is testing all the coefficients, might be easier to ignore that table. You can see here that it's giving you the regression equation for the different genders and levels of abdominal fat. This is how you would actually calculate out a predicted cholesterol value for someone based on this model. And it also will give you a couple of warnings about unusual observations. If you just have a couple of them, it's probably okay. If you have a whole page of them, 20 or 30, that might be a bit of a problem. Okay, so before I stop, I will just have a look at this interaction term. If you find a significant interaction, it's really, really important to do a graph because that will help you interpret what's going on. So to get the graph for that, you actually go to Stat, not Graph, and go to ANOVA, and we can see here we have the option to do an interaction plot. Now I've already put this in previously, so you can see that our response is cholesterol and our factors are gender and abdominal fat. That was my knee bumping the table if that came through on the audio. So what we've got is that as you have greater levels of abdominal fat, your cholesterol on average is also getting higher. But the difference is we've got men with the squares and females with the blue circles, that this abdominal fat seems to be having a bigger effect on the men's cholesterol than on the women's, because they start off fairly close together, with both have fairly low cholesterol with low abdominal fat. Then with some abdominal fat, they've both increased, but the men have increased more. And then again with the severe abdominal fat, it's had more of an effect on the men. And so when one factor has more of an effect depending on another one, that's called an interaction. You must look at the p-value as well as looking at the graph. Sometimes it can look like you've got an interaction, but it's not significant. So you must look at this together with the p-value. I'll just scroll back up, which is there. If it's not significant, you can safely take that out of the model and run it again. And in this case, I would leave it in there obviously because it's significant, but I might take out the age and run it again.